Will so today we begin and sort of end our study of the ideal Fermi gas at by studying the specific heat at low temperature. So we have set up the whole thing, but we just need to work out some details, and that's what I'm going to do today. And so this was our goal when we started the Grand Canonical. So our original goal several weeks ago was to show that the specific heat CV for a metal goes as some constant times this sum temperatures, and this was the ionic contribution. Now we know we are very sophisticated with a contribution of phonons. Okay, and today we will see this part, which is coming from the electron gas. Okay, so this will sort of be a nice conclusion to something which we set out to do. And so one thing which you people at your level, this is a fairly advanced course in the sense that you are in your, some of you are in the master's program. So all of you, I mean, it's not a BSc first year, second year level course. So the mathematical level that is required is higher. And so these things, so we cannot do things exactly anymore. It might make you uncomfortable, but I would recommend that you get comfortable with working with the big O notation, approximations, etc. And one more thing which I've been asking you to do is to plot things. And I think these are two methods. Sometimes you should plot by hand, but nowadays you can plot it on the computer. But even that takes skill. I mean, you need to know how the general behavior will be. How do things behave at small values or large values of argument? These are the kind of things that we need to do. Okay, so in that sense, today's lecture will be slightly messy, but I spent some time this morning and I cleaned up the presentation, so it will be kind of sanitized version for you. Okay, so the equations of that are relevant, we have actually worked this out already. The first one is just 1 by V, but I'll write it like this. We had an expression for 1 by V, right? Lambda cubed was equal to F 3/2 of Z. Okay, where this F function we already defined. The second equation, which I wrote is the equation of state, but we know that P equal to what? 2/3 little u, right? So we can, but since I'm interested in specific heat, I won't write P, I will trade that for U. Okay, so we'll get something like U by V. Okay, is this 2/3 will go to the other side, become 3/2 or whatever. Okay, this is little u. Okay, it will be 3/2 kBT. Okay, divided by lambda cubed F5 by 2 and so on. Where this Fn's, I don't have to define it again, hopefully. Okay, or maybe let me. Okay, so this is the definition of all these guys. Okay, so and lambda is the thermal wavelength. Okay, so we have these two expressions, and so what I will do is I will divide out the second expression by 1, where I will get u by, so let me just do that. Okay, so if you do that, so I'll write that as 2 prime. Okay, little v is what? Capital V upon n. So if you just divide out, you will get u by n is equal to 3 by 2 kBt. Okay, and so we can trade lambda cube for v f3 half by 2. Hopefully I have not messed up, but I think I'm not. Okay, this is what we get. So these are our equations, and so what are the things? So we need to do a couple of things. We need to solve for mu. Okay, so that we are going, so that we can connect up with results in the canonical ensemble where n number is given. Okay, so and for that we will use equation 1 is sufficient. So it's an implicit function. Okay, so equation 1. Okay, so what is that equation? It says lambda cubed by little v equal to f3 half of z. And before that, we need to ask what is the limit we need. So we are interested. So the key point here is at low temperatures. And we have to define what we mean by low temperatures, and it will come out naturally. Okay, so low temperatures, what we will see equal at the end of the day is that it will be a ratio of two energy scales, and one is kBt, and the other is the Fermi energy, which we saw. This is what which is what we used fixed last lecture by setting it equal to the number of particles by the number density, right? So this guy must be much less than 1. Okay, this is what one means by low temperatures. And because of this combination, I'll just define this combination to be little x. Okay, so x is less than 1 at low temperatures, and actually even low densities, blah, 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 all those things are there. At low temperatures, we expect z to be much, much greater than 1. Okay, so we need expressions for f3 half, and the next one is f5 half. So for f and z for large arguments. Okay, I wrote something, I copied something from a book, but we don't need to copy. We will derive it today. Okay, so we'll do that. Okay, so at low temperatures, we need to derive expressions for this. Okay, so this is the first thing we need to do. But then this is not, we are not done, because this is a series in, it will be an expansion, and what we will need is that we have to do an inversion. We will need to invert. Okay, so it will be a series. We will obtain we already saw Fn of Z for large Z when some, okay. So one thing we will see is that, in particular, we'll see that Fn of Z, the leading term is log Z power. This tilde means there are proportionality factors, everything. The dominant thing power n. Okay. We'll prove this. Okay. Okay. And then it will, actually I can even write something. So plus 1 plus some constant times log Z power minus 2. Okay. Star means star is some unknown, undetermined constant, and it depends on n also, whatever what that is. Okay. So we will have this kind of structure in the problem. Okay. So if this is for large. So there are some approximations, and so we will see this thing. So this is the structure. So now you can see that if Z is large, log Z is also large. So 1 by log Z is small. Okay. So first thing is, you notice here that there is no, the next term in this should have been 1 upon log Z. There's no log Z inverse, and that will turn out to be something related to the evenness of some order. So only you will have even powers of 1 by log Z. Okay. And actually it's not this plus some exponentially suppressed terms. Okay. Terms like order e power minus Z. Okay. So this is the full structure of any of the Fns. Okay, we'll say n, probably some n greater than some number. Okay, n greater than 1 maybe. Okay. So this is the structure. So but we need, so that's what I'm saying here. We need to, but we want to, so if you are going to solve for mu, that's like log Z is nothing but beta mu. This is beta mu. Okay. So temperature is given, so that once you know log Z, you know mu. Okay. So, but the point is that we want to solve for mu, but we have a series in beta mu. So we have, but we know, one thing we know is that beta mu is large. So 1 by beta mu is a small quantity. Okay, so what you can see is that you can do, this is the kind of thing where you can solve things recursively. Okay. So is this clear? This is the structure. We'll prove this. So now coming back to this equation. So what we can do here, if you look at this equation, it just says that lambda cubed upon v, this is some known quantity. If you expand this thing, now this is a series in yeah. Z is large, log Z is large. Beta mu is log Z.
So we are seeing low temperatures. So because of low temperature is getting like
it is large. It is large. Even mu will, I mean, at the all I'm saying is Z is much greater than 1. It doesn't affect anything. Z is much greater than 1, log Z is also much greater. That's all. Yeah, I mean, one shouldn't lose sleep as to what is being tuned. I could keep, for instance, temperature fixed and, play with the increased density. Even that will do stuff. Okay. So, all I'm saying is that I need Fn of Z, this function, for large arguments. This is not a physics. I mean, physics tells you that Z is large, but what I'm saying is that this statement is a mathematical statement. It's just a large argument behavior of F of Z. But we need to use this because we want to solve for Z. Okay. So the point here is, so how are we going to solve this? Okay. So, good. I wanted to do something. Okay. So let us, so for example, I will write the answer for F3 half. Okay. So that we can, F3 half of Z equal to, I have it somewhere. This is what we have. Okay. So this, let me also tell you, this pi square comes from zeta of 2, which is pi square upon 6. Okay. So this is actually, we will see later for general Fn that this coefficient star will have a zeta of 2. Okay. With some independent factor, but zeta of 2 will be there. Okay. And this is some gamma of, this is gamma of 3 by 2. Okay. So now we have this thing. So now we have to go ahead and solve. We have to solve for this thing. And so the way we will solve it is as follows. We will say that mu equal to, okay, one more will be equal to two constants. I'll just call them A0 plus A1 into T square I'm converting it into energy in a short move. Okay. Plus, so in principle, it could have had a term which is linear in T. It won't be that because there is some symmetry which is there, which we'll see in a moment. You can even put T and you will find that it becomes that it will be 0. Okay. And so we know that one more thing which we sort of know, but we will solve it. We know that at T equal to 0, mu equal to epsilon F, Fermi energy. Okay. This implies that A0 is epsilon F. Okay. So what I will do now is I will write mu not like this. I'll write it as epsilon F into 1 plus. So I have to define some new coefficient. I'll just call that A1 tilde times x square, where x is kBt by epsilon F. Okay. So I'm just redefining these constants, but we have already got an expression for epsilon F. But in this method, I will get the epsilon F again. You can go back and check. Is that correct? Okay. So what we have, so the equation, so now the equation lambda cube by V is equal to F3 half should be written as follows. It should be written as beta mu power 3 half divided by, what was it? Some 3 by 4, whatever. 3 by 4 root pi Okay, here we have to go and put this value of mu into this thing. Okay, and we only want to work to second order. Just remember that. Okay, so if you look here, so beta mu will be beta epsilon F. So this will be equal. So what we will get is lambda cube by V is equal to beta epsilon F power 3 by 2 divided by 3 by 4 root pi into, okay. So now we have pulled out this thing. So this will be mu by epsilon F power 3 by 2. Okay. So this is what we have. I just want to do one more thing. So you can see here that what is 1 by beta mu? Okay. 1 by beta mu is 1 by beta. And what is beta epsilon? What is beta? So beta epsilon F, this implies that beta epsilon F is 1 by x, right? So 1 by beta mu is x. Okay, so what you can see here, x into 1 plus so this term is order x, and this is also giving this thing. So 1 by beta mu will be 1 plus this order x cubed. So I'm only keeping terms to order x. Okay, so what it says here, so that actually is an essential simplification. It says that in this term, I can replace mu with epsilon f. That's what it's saying. And the error will be absorbed in this ellipsis, the set of terms we are dropping. Okay, so this is the O working. Okay, O magic working. So I can write this as x square. And this, of course, I have to work to order x square. And this will become 1 plus pi square upon 8 x square power 3 by 2. Okay. So let's go ahead and substitute this. And so we get lambda cubed by V equal to again in binomial expansion, since I'm working only to order x square, I just need to take the first term in the binomial expansion. Second term will be x power 4. So I throw it away. Okay. So 3 by 2. So that becomes 3 pi square upon 16 x square into okay. Something is wrong. Some number is wrong. Just give me a second. So mu we don't know. Mu we don't know, right? Mu is some we called it A1 tilde. No, I think people are. I wrote this. We don't know this term, right? Right? We haven't solved for A1 tilde yet. We need to. Okay. So this is the equation that we have. So first thing we look at order x power 0. That just says throw away all the x square terms. This is 1, this is 1. So this just says that again, I mean, you people are sleeping or what? I don't know. Huh? That is, I put. I forgot to, I keep forgetting to put. It is this, right? Okay. So zeroth order just says that, which is kind of nice. It says that lambda beta. So I can take this to other side and it becomes, it comes lambda kbt. Okay. So I'm just taking this guy to the other side. Okay. Divided by V. Then you have to multiply by this into 3 by 4 root pi is equal to epsilon f power 3 by 2. Okay. And we know that epsilon f should not, it's the zero temperature guy. But on this formula, there's a t out here. But if you remember, that's in lambda, there's a 1 by square root of t. So the t powers go off. Okay. So this lambda square root of, you know what that is. So compare with the answer yesterday. Huh? Cubed now. Yeah, it should be cubed. Thank you. Okay. So okay, compare with yesterday's. Okay, I have not checked, but it will agree. Okay. But now we have to do the next term. Okay. So we need to compute. But the best part here is that left-hand side of this equation is independent of x. So we just need to require that so at order x squares, LHS is 0. It has no dependence on the constant. We have used up that, okay, by the 0th term. So it just says that, so if you at order x square, it just says 3a1 tilde by 2 plus pi square by 8 equal to 0, which implies a1 tilde equal to minus pi square 2 4 by 12. So we get our formula. Okay, there are exponentially suppressed terms. I'm not bothered. So this is the answer. Is this correct? Yes. Okay, good. So now you can see we have inverted the problem. But this method is so general that you can put another a2 tilde x power 4 and you can solve for it. But now it will get a little bit more messier. You need to, you will get contributions. Here I just replace this thing by x square. This will get some extra terms. So you'll have to collect terms and solve it. It's like a recursive thing. But we don't need beyond this. Okay, so this is so we have finished. So we have concluded. So we now have determined mu to next to leading order. Okay, so we want to do the same thing. Okay, so now so we have this. Next, we need to do the same for u. Okay, because we want to get its so the leading term will be just some zero temperature energy. What is the correction? And that will be again will be order t square because of the symmetry thing. Same thing will happen. Everything will come as a function of x square. And so if you take one derivative, you get your linear thing. So once we get the quadratic piece, so we need to do it too. Okay, that is obtain the next to leading order term. Okay, so for this, we will do this u by n is equal to some 3 by 2 kBt into is there any other factor I'm missing? Nothing, right? That's okay. So now what we need, so we need to, so what really we need to expand, if you wish, to compute the ratio. For large Z. Okay, we already have an expression for phi 3 half. So I'll write another expression for f5 half, and then we will derive some general formula which will agree with this. Okay, so we'll finish our computation. Okay, so again, f5 by 2 of Z equal to the expression somewhere. But life is easier now because we already have solved mu. So we just have to plug in mu and only keep terms up to x square and nothing more. By some gamma is there. So that is 15 by 8. I think this is gamma 5 by 2. Okay, there is some cancellation, but I've written it this way. Okay, so we want this guy to order x square. Okay, so again, as before, this term, so we can write this thing as, no, let's first divide it. Beta mu divided by, this will be 15 by 8. F3 half, what did it have? 3 by 4 or 3 by 4. Okay, so we are done here into, let's simplify this. So this is 5 by 8. Okay, and like before, I'll just write this as x square. Okay, and we know beta mu, we know again. So we can write this as 3 by 4. Beta mu, we can replace, so this can be written as, beta mu was 1 by x, right? 3 by 4. Let's simplify things. Sorry. So what is this constant? It is 8 by 15 into 3 by 4, 5, 2. So 2 by 5. 2 by 5 beta epsilon f, okay, into mu divided by epsilon f, which is 1 minus, mu is 1 minus pi square upon 12 x square into 1 plus 5 pi square upon 8 x square. Again, this beta coming around is good because what we have here is a kBt. So the beta kBt should go away, and so t equal to 0 should, the leading term should be independent of temperature. We know that. Okay, so that's what we get. So we get 2 by 5 into this beta epsilon f into, now with just to x square, you just have to add these coefficients. So 1 plus again, I'm unhappy with what I have, but right now that's not the key. Oh, I made a mistake here. How did I get this? This is the only, this is the mistake here. Now I remember is that I have to also, this is f5 by 2, but here I have to divide this by f3 by 2 also had something, right? It was 1 plus what? Pi square by 8. Thank you. Okay, so that pi, so it'll be 5 by 8 minus 1 by 8. 1 plus, right? F 5 by 2 is 5 by 8. That is correct. So 5 by 8 minus this thing is 4 by 8, is it? 4 by 8, which is a half. I think now I'm okay. Sorry, I'm not so perfect doing calculations. Okay. So this will be, so now you will see that this is 6 by 12 minus this 5 by 12. So we are now done. So we get f 5 by 2 by f 3 by 2 is equal to 2 by 5 beta epsilon F into 1 plus, okay, plus sign is important because we want CV to be positive. Okay, so 5 by 12. So we have got this. So we can now, we just have to multiply this by 3 by 2 kBt, right, to get that. So U by N is equal to 3 by 2 kBt multiplying this. So this will just become 3 by 5 epsilon F. So dimensionally, you can see that it's dimensions of energy. So the betas went away into okay. So this is the final answer, which I believe is correct. Is it correct? Yeah. Okay. So again, you can go back and just compute. So verify that the constant term is as expected. Because this is very easy to do. You have a bunch of, so you think of, go back to momentum space. You have a bunch of particles which live in. We can take all values inside the sphere of radius pf, where pf square upon 2m is epsilon f. So you just have to do counting and multiply it by the energy, which is okay. So that's all. So you can just do this computation. It's a simple computation. You can check that this is the correct answer. Okay, but what we have, so we have seen this thing. So C by N will be, you have to take a derivative of this with respect to T. So that will be 3 by F 5. Okay, so 1 T will go off. I'll pull the KB here. Okay, these epsilons will cancel into 5 by 12 pi square into 2 kBt. So let's simplify this. 5's cancel 1/4. This is okay. So the coefficient. So we get that the coefficient of T is this quantity. Okay. So question to you is, what is this ellipsis will have a correction term, right? What will be that term? What will be the power? Huh? Pi square also, right? Yeah. Thanks. Okay. So what will be the next correction in C by N? Yeah, louder, everyone. I can't hear you. I could read your mouth. Order T cubed, right? So really, if you want to compare with experiment, we need to do the cubic term because we have to remove it to get the AC. So the cubic term has the ionic and the electronic contribution because T dominates. So we need to know the sub leading term. So if you really want to match with the experiment, you have to do these things. You need to, you can't stop like we did here. You need to do the T cube term also. But it is kind of not very hard. It's just the method. We have to do one more term. Keep terms to order x power 4, and then you're done. Okay. So I'll pause here for questions. So now I will just I'll write a formula and I'll tell you how we prove it. Okay. So I'll be very schematic, but that's good enough. So go back to the definition. Okay, and z is supposed to be large. Okay, so that's what we want. But so this function 1 by z inverse e power x plus 1 is the Fermi function, which at t equal to 0, so we know this function okay is such that, so if you remember, I drew this. So this is for t equal to 0 or z equal to 1. But for the case when t is close to 0, so this is small t, you can see that this function will agree here. So if you take derivative of this thing, you get a delta function exactly at mu. This function. Okay, x. I mean, this is called beta mu. Okay, so this is what we will get. So one thing you can see, if you take a derivative of this at t greater than this thing, it will have only support near mu. Okay, so if you take derivative, the derivative support close to, and width is around kbt. You can prove that. Okay, so I mean, this diagram doesn't show that. So mostly it will be 0 if you go far away. So what you do is you integrate by parts. Okay, so to take advantage of this is integrate by parts to express Fn in terms of derivatives of. Okay, so I'll write the formula, and it's a very simple integration by parts. I just have the formula here. Okay, so this function e power x square, sorry, this function e power x by this thing whole square, z inverse e power x. If you take x2 minus x, you will see that it is symmetric. You can convince yourself. Okay, because this will become e power minus x, so you multiply numerator and denominator by e power x, it will work out. Okay, so you can prove the symmetry property I was claiming. So this you have. So, but nice part about this, that this integrand, okay, ignoring x power n, okay, has support when e power x z inverse equal to 1 or x equal to beta mu. And it is a sharply following function. So really, so this thing will have supports in some this thing. So we can make a change of variables. So we'll make the following change. Let y be equal to x minus beta mu. Okay. Then what you will get is Fn There is just simple change of integration. So now what we will do here, so yeah, so now is where the symmetry actually, now is where the symmetry is much more obvious. You take y to minus y. Really, it's about this thing. So this integrand, again, so it is y goes to minus y is a symmetry. Okay, this term will flip. So because of that, you can write this as beta mu power n divided by gamma of n plus 1 into integral of, now I can do binomial expansion. This will be n y by beta mu plus n into n minus 1 by 2 y square by beta square mu square plus dot 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 times e power y dy divided by, okay, because of evenness argument, the linear term will drop out. The integral is 0. Okay. One more thing which we can do is, if you look here, what are the limits I didn't, right? So the limits here will be from minus beta mu to infinity. But mu is very, very large. Beta mu is very large. So you will find that if you look at the integrand, it's exponentially suppressed. Okay. And it goes like order e power minus beta mu. So it's exponentially suppressed. So this I can replace with minus infinity. Okay. And add order e power minus beta mu by adding that. So we are throwing away terms which are of that order. Okay. So we have this, and so you can go ahead and you need to do these integrals. These integrals are not so hard. Okay. So you can do this. So you need to do some integrals, in, which is integral now minus infinity to plus infinity. Okay. So there are general answers. So for I0 is 1, for n greater than 1, 0 rather. Okay, and yeah, so in equal to 0 for n odd. Zeta of n. Okay, so in particular, I2 is what we needed. I2, you can see this is 4 and this will be half. So it is just 2 gamma of 2, which is 1, zeta of 2, which is equal to pi square upon 2. Okay, so this completes all the, I've done the integrations. I'm not proving this. I'm writing this answer. So we get a nice formula which says that, okay, f. So we can now obtain the expressions for f3 by 2 and f5 by 2. What you will see, so even before we do the integration, we get our structure. You can see we got this fat term. So if you remember, I wrote beta power mu power n. In fact, if you put this gamma, so on and so forth, and then this y square piece is what will give the x square term. That's it. Doing this, you get a 1 by beta square mu square. So this whole structure which I wrote is evident before you do anything, which I wrote somewhere long ago, which is here. Okay, so I could have been more sophisticated and written gamma divide by gamma of n plus 1. I could have done that also. Okay, so this is just gamma of n plus 1. So the rest of it, you can see that. So I told you there is zeta of 2 also coming. And if you see the n dependence is also n into n minus 1. So you can put those, I mean, you will find everything work out. So it's kind of nice. So exercises, so I'll conclude with an exercise. Compute the t cube term. Okay, so I'm done for today. Are there any questions and comments?